Okay, good morning. So today I'm going to cover Edsim. I'll give a tutorial on this simulator which we'll be using for doing your project. You can download Edsim from Edsim51.com. It is a Java app, which means you get a .jar, J-A-R file. And you need to have a Java runtime environment, which most computers should already have one. If not, install Java. I shouldn't have to tell you how to install Java. And it should be cross-platform. So it should run on Windows, Mac, Linux, anything that can run Java. And there are probably two versions on that website. So one is the DI and one is SH. DI is dynamic interface, and that is the standard, and that's probably the one you should use by default. And if you want to customize, you can use the SH version, which allows you to put up the widgets you want, and widgets you don't, you can remove those. And so that is something you should be doing right away and start playing with it. And so Edsim 51 DI looks like this. So it is a Java app. And what it does is simulates an entire embedded system. Okay, we talked about embedded system last time. So it is a special purpose computer. It's not your general purpose PC or server or anything like that. It's more of a handheld device, right? Think of it that way. Tiny little processor, but you could write program to it. And then what the program does usually is more controlling these peripheral devices. So here you have what's called LCD, that's a liquid crystal display. So that's a two-line little display. You might see they may have backlight or may not have backlight, and you should be able to display characters on it. So the LCD is over down here. This little widget at the bottom of the screen, that's an LCD. Okay, and then there is LED. LED, you probably know. So these are 7-segment LEDs. Right now, if it's white, that means it's not turned on. It's red, that means power going through it. It's lit up. But yeah, you'll figure out. And keypad is more like this, what you have on the telephone dial, or right. This is more like a telephone keypad. Okay, this thing. And so it has 10 digits plus a star and pound. And a bank of buttons, so that's what these are. So the 0, 1, 2, 3, 4, 5, 6, 7, those are individual buttons you can press. ADC for analog to digital converter, DAC, digital to analog converter. So ADC takes a voltage, turns into a number. DAC takes a number, turns into a voltage. We probably won't be using that as part of the required part of assignment, but we may give extra credit or have an open part that you can play with it. I haven't done any on this system to use ADC, DAC, but maybe you can think of something you can do on your own. Now, these are the peripherals. Okay, so that means these are the little devices for input and output purpose outside the processor. But there is a processor that's not shown here. That's what you'll be writing the program for. You'll be writing the firmware for it. Oh, another thing I didn't mention is this is called UART, or serial port. The reason I didn't mention it was because it's not considered what's called a peripheral, in the sense that it's not an extra chip on the outside. It's part of the processor. In fact, it is really part of the instruction set. So that when you want to read the serial port, write the serial port, you actually read or write a register that's associated with the serial port. And then it causes the bits to be shifted in or shifted out. And that's how a little embedded processor can talk to, say, a PC or another embedded processor over like a single wire or 2-wire type of interface. Okay, so that's kind of a quick overview of its capabilities. Well, that's the part being simulated, but the whole thing is actually more than that. Okay, so that it actually supports display of the processor state. In fact, it even has an assembler built in. You can write assembly code in the window, directly type it in, have it assemble and run. So very convenient. Now this other one is the Edsim51 SH as opposed to DI. DI was what I showed. That's the complete one. SH is more of this customizable. So for now, it only displays that the serial port. Oh no, this is the general purpose I/O port, and this one has only very simple target with a 1 LED. So if you don't like that distraction, like on the previous page, that's wow, so many things I didn't really use. Okay, you could customize it, so rule out some distractions. But that's only if you have time to play with the customizing. Okay, I'm not gonna show you how to customize your own interface here. Okay, so once you install it and it's up, you see that whole screen. You can start writing your hello world. Now, well, here you don't have hello world, but hello world here is lighting up that little 7-segment LED. So first program, you can type in the following 3 lines. And in fact, there's only one instruction. There's ORG and then 0000H. And then the only instruction is this move, MOV, no E, MOV, and then 90H, comma, #24H. And then end. End is not really an instruction. It's called a directive, assembler directive. So this Edsim assembler actually will tell you or use syntax highlighting to indicate what is an instruction versus what is called a directive. Okay, so a directive basically is directions for the assembler. It does not translate into actual instruction for the machine, for the target machine. Whereas if it's like a blue type of thing, then yes, that actually corresponds to an actual machine instruction. Okay. Now, how many bytes does it turn into? Well, it depends. We'll see that. And in fact, I include a data sheet so that you can take a look and even hand assemble if necessary. I mean, you should do that sometime just for fun. Anyway, and then what you do is you type in these 3 lines, type ASSM, that's short for assemble, as a verb. That means translate from the text into binary, okay? And once you do that, the machine can run it. The machine only understands binary, doesn't understand text. Well, that's what an assembler does, it does a translation. Then once it's assembled, then it changes the look. Okay, so before it looked like this. After assembling, it shows this 4-digit red 0000, a bar, and then the same instructions that you saw, but shifted a little bit. I mean, if you didn't indent. Then now you can press a run, and you should be able to run. And what does it do when it runs? It turns this, can you see it on the bottom? That 2. Well, if you can look carefully, yeah, that is a 2 with a dot. Okay, so that's like an LED turning on and displaying the 2. Now you can see that. All right, so let's try this for real. So if you open up Edsim51, this is what you'll see. So we do org 0h, okay, and then move, what is it? 90h, right? 90h, comma, and then 24h, but with the pound sign in front. I'll explain what these mean in case you haven't seen. So exactly as shown, click assemble, just zoom in, assemble, yeah, exactly as shown. And then now if you take a look at the bottom part is all blank, right? Nothing lit up, nothing in red. If you click run, aha, see? Now it shows a 2 dot. Yay, that's our hello world. Right? So assembly language, not very hard. You can write it. One single instruction, right? So don't be scared of assembly. Not that hard. You can think of it as tiny little programs, tiny functions. And they have funny names, but each name is really the instruction. And you see, wow, okay, I just click running, and occasionally it's showing a little garbage, or it's flashing. If you notice, And this flashes a little bit, and then flashes a little bit, and comes back. So what's it doing? Well, if you look, the program is still running. How do you know? Well, look at the PC. So anybody who's taken computer architecture knows PC stands for program counter, not personal computer, okay? Program counter. Right, that means where are you in the program? There's a little register that points to that has the address of the current instruction, right? So it is at one address at a time. And once it finishes, increments, right? And then if you jump, it sets it to some other target. That's how it works. So the PC is still running. How come? Well, because we don't have an end or exit. The machine only sees what? It only sees this instruction move. At what address? At 0000, and that's a hex. Okay? What happens after that? When it sees, does it even see end? No, an end is directive for the assembler. Assembler knows, okay, that's the end of the program, fine. Okay. But what does it do after that? Nothing, right? So memory has whatever garbage already in there. And what's in memory? Well, in 8051, they have what's called data memory versus code memory. They're in different address spaces. So if you see here, you see memory data, and then if I click, it says, oh, click to change between data memory and code memory. Okay, so let's click it. It's not going to blow up. It's just click. Okay, what do you see? You see, so you can probably guess what this means. So that's the high bit of the address, 00. Now, 0000, that would be a start of memory, right? So the instruction got translated to the top, right? So, and you remember we did a move of 90 hex to 24 hex? And if you stare at it, hey, that looks kind of familiar. I didn't recognize 75, but I recognized 90. I recognize 24. Those are pretty much you might call, okay, for software people, arguments you pass to this little function. Well, in machine terms, it's the operands for the machine instruction move. So you can probably guess, with intelligent guess, 75 is that move, 90 is that 90 for the first parameter, or first operand. 24 is that second. And these are displayed in hex, right? Because, well, here, that 90H, 24H, that H is hex. It's like, oh, well, what kind of syntax is this? Well, this is Intel assembly syntax, okay. So Intel did this at the time when, I mean, that was their convention. So they put some numeric literals followed by the base. And if you don't put the H, it's treated as decimal. If it's the H, interprets it as hex. And when you work with machines, you're working with bits, so hex is convenient, right? You should be very comfortable knowing what binary for 9 is. Anybody? 1001. What's C? Well, okay, go back and memorize these. Kind of like multiplication table. You should be very comfortable going back and forth between bits and your hex digits. Okay. And so that is just a single instruction. So okay. So then what is it doing? So you see PC is, well, this is not refreshing every single instruction. So it's once every couple, I don't know, a few hundred or a few thousand. So it's a snapshot, it's a sample point. So it looks like it's cycling through the memory, right? And how many bits are there in this memory? There's 4 hex digits. So that makes it, how many bits? Not 64 bits, 64K of space. 16 bits. 2 to the power of 16 is 64K, right? 65532, right? So that means the program memory is 64K bytes. Okay, and that's a 16-bit address space. Okay, you shouldn't know this. If you don't, you probably shouldn't be taking this class. So anyway, so what's it doing is going from beginning of memory running all the way to the end and then comes back again, right? Why? And then what's it doing? Well, all zeros. Now, what does it do to, what does it do to a zero? Well, zero turns out to be what's called a no-op. Everybody knows what a no-op is? A no-op is a machine instruction that does nothing. It's like, well, why would you want to do nothing? Well, all machines do this. All machines include instructions that do nothing because for whatever reason, because compiler might need to jump to a target where it has nothing to do, but just so that it can flow through, right? Or maybe some people use it for delay purpose. Otherwise, other parts where they might use it for what's called allowing instrumentation. So that you go in and then you leave a bunch of no-ops, and that's your program code. And if you want to start logging or do debugging, set breakpoint, whatever, a debugger or these loggers, they can go back, modify those no-ops, turn into some useful instruction so that you don't have to relink your program. Okay, so no-op is done for a lot of purposes. Now in this case, 8051 happens to define 00 as a no-op, which means it doesn't do anything. But then it actually does something as a side effect, which means the program counter says, oh, no-op, then move on to next, and next, next. So that's why it cycles through the entire memory, then comes back up. Why? Because it ran out of bits. Once you reach the last instruction, the FFFF, what happens? Well, you increment even 1, 0, 0, but then there's no 1. That 1 doesn't fit, so it comes back to 0. Right? So that's why it's cycling through. Okay, so you never knew that a single instruction assembly program requires this much knowledge, right? But, well, that's what you should know from this very simple program. And if you know the concept, then everything else kind of builds on it naturally. It's not as difficult. So don't be afraid of writing assembly programs, but do get your hands dirty. Do try things. Check your understanding. That's really the only way, because there may be tiny little detail you didn't know, and I may have said it, you didn't catch it, but you won't get it until you try it. Okay, so you may end up spending some time saying, why doesn't this work? Well, because you're missing 1 bit somewhere, right? But this is nice because it gives you complete view of both program memory and data memory. Data memory is all blank. Okay. All right, so that's our hello world. We can pause it now and switch back to our slides. Okay, so that's first program on bare metal. Bare metal means you write the code directly for the machine, no operating systems. And in this course, you get to write a little bit, a toy operating system, but you might be, so don't underestimate how much work it takes to write a little toy one. But once you've done one, you run successfully, you'll know the concept to write a real one. Okay, so, but if you jump into a real one, I think that's just too overwhelming. And besides, you'll probably be given a lot of code you don't understand and just run it. And I don't think that's all that helpful. Here, be sure you understand completely, 100%, what's going on. Be able to explain every single bit. Okay, that's what it takes. And if you're missing 1 or 2, it just might not work. Okay, now how does it work? So you need to know a little bit of hardware, and don't be afraid of hardware. Hardware is not that hard. Even though the word hard is in hardware, it's not hard. It's actually much simpler concept. So what happens here is the 8051 microcontroller, which means it has a core plus some built-in support for input-output. It supports what's called general purpose input-output ports, or GPIO. And it has 4 ports, P0, P1, P2, and P3. And each one is connected to 8 pins. What's a pin? If you look at a chip, right, you see this metal little legs on the side, kind of like a bug, right? The metal, that's a pin. And a port, in this case, is a group of 8 pins, okay? Because, I mean, when you read or write, you want to write byte at a time, right? So 8 in a group is kind of a natural unit, okay? And so what we did was, remember, move a 90 hex comma #24, right? So first, the 90 hex. What does that mean? Well, 90 hex is actually an address. It's the address of a what's called special function register. But think of it as a register. You know what a register is, right? On a processor, it's a little bit of hardware storage unit. You probably know these as R0, R1, R2. Those are general purpose registers. Or in MIPS, they get $0, $1, and all those things. Well, they don't have to be all general purpose. They can be special function. What that means is they don't just store values, which is what a regular register does. A general purpose one stores temporary values so that you don't have to go to memory each time. Now, a special function register stores value but causes side effect. What kind of side effect? Well, in this case, the side effect is you put the pin value, you set the pin to be high or low voltage based on if you write a 0 or 1 bit. All right? So if I write to P1 as a special function register, which is at address 90, then what happens? Yes, there is a little register. It remembers the value you put in. But as a side effect, the bits that you put in show up. So you can measure, you can put a probe. Is it high voltage, low voltage? Or you put a light on, light off, right? So, and what value do we put in? Remember the move instructions? Okay. Remember we put 90 hex, comma, 24 hex. And then there's a #24 in front. So 90 is, think of it as an assignment statement, right? So 90 is really the address for port P1. So P1 gets the value 24 hex. That's how you should read this, okay? So think of it, I mean, C, you would write it P1 equal sign and 0x24, okay? Now, so the # here is what's called an immediate sign. But the word immediate doesn't quite make sense here. Think of it as a constant number to be distinguished from the address. That makes sense? So 90 hex without the #, that refers to the address. Good. And if you have a # in front of the value, that does not refer to address 24. It refers to value 24. So what you should do, or what the machine does, is it puts the value 24 hex into the address, the register at address 90 hex. Does that make sense? Okay, so what that does is, well, P1 is not just an internal register. You can actually see it on the outside. So if you take a chip, say, oh, P1. You can, well, there's actually 8 pins. So here, P1.0, P1.1, all the way to P1.7. What does that mean? Well, bit 0 of P1, bit 1 of P1, bit 2 of P1, all the way to bit 7 of P1. Okay? So whatever value you write shows up on here, on the pin, on the outside, so you can measure it with a probe. You see a voltage, high or low voltage, 0 volt, I don't know, 5 volt or 3, whichever supply voltage is. Or you put a light bulb, turns on, turns off, right? Okay, so that's the side effect of these special function registers. So what bit do we put in? 24 hex. What's 24 hex in binary? Oh, you gotta know. 2 is 0010, right? And then 4, 0100. Not that hard. Okay, so what does that do? So that puts the value 0, well, 2 is 0010. So, oops. Yeah, okay, sorry. What happened? Here. Okay, there we go. So you see the 00100100 binary, okay? But then how are they connected? Well, guess what? These bits or these pins are connected to the 7-segment LED individually. So that allows you to use P1 bits to decide which segment of the LED to turn on and turn off. How are they connected? So, well, you can check the connection, right? So they have these named connections. Segment 0, 1, 2, well, sorry, this is a little pixelated. 3, 4, 5, 6. So it kind of goes top, and then left, right, middle, and then the left, right, middle, and then finally the dot. There's a little decimal point, right? Okay, so there's the connection diagram. And so if you put 0, 0, 1, 0, 0, 1, 0, 0, well, this is a little bit counterintuitive for software people. If you put a 0, it turns on the LED. If you put a 1, it turns off. It's like, what? Why? Well, there's a reason. Because these things, LED is one that needs power. It's not just a logic value. GPIO or these pins are supposed to indicate a logic value. So they may go from 0 to a high value, but they don't have a lot of current. So even though they can have a high voltage, if you don't have enough current, that's not enough to turn on a light. So you don't want to use the chip, or you don't want to use the microcontroller as your power supply for the LED. Instead, what do? You do the opposite. If it's outputting a 0, what does that mean? That means the processor or microcontroller connects to ground. That's easy. That's the connection. I don't have to drive so much value. I don't have to develop so much current, right? I just have to connect to ground. And so that means a 0 is so much easier for a microcontroller than a 1. And so if the LED itself provides the power, then yeah, I just have to decide if it's a connected to ground or not connected to ground, right? So as you can see in the schematic, this decoder with this transistor, so that means it's giving power. That's a kind of a power switch, but okay, you can think of it as a power supplied by the LED, and then each one goes to this. So in order for light to turn on, you have to have a voltage difference, right? One part has to be ground, one part has to be supply. Well, because it already has the supply power part, so processor's role is different. It's opposite. It's to provide ground or not ground, right? So that's why if you program a 0, that establishes a ground path, and that's what creates the voltage difference, and that's what turns on the light. Okay, so in here, if you want to turn on a segment, write a 0 bit. If you want to turn off, write a 1 bit, because it's deciding whether or not it's connected to ground. Okay, that's a little backwards. That's a polarity issue, but shouldn't cause any difficulty. So with that in mind, you should be able to create the 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, or other funny symbols that you want that are not digits. And some people have variations, like 7, they might have a 7 over here, 6, they might have another turn, 9, they might have another turn, and so forth, right? So there's not one way to do this, but you should be able to try different values, predict what you're gonna get, try it to see if you really get the LED to light up the way you expect, okay? Okay, now, so now back to the assembly. So this is the little assembly program we saw. You see ORG and you see END. So remember again, these are what's called assembler directives. They are instructions for the assembler, which is the translator, not to translate into the actual machine, okay? So ORG is short for origin. That means where do you start putting the assembled instruction. If you say ORG 0, that means, okay, when I start translating these, I start putting it in address 0. What if you want to say, okay, I want to do something else, okay? And all right, the org, okay, reset. Can I reset? Yeah, okay. If I say 70, how's that? And I assemble, it shows me that's 70, right? And if we go and take a look at code memory, so you see, we used to see 75, 90, 24 here, right, at 0. Now it's down to 70. So 75, 90, 24. So org tells the assembler to start your instruction at a different address. That's what org does. So it's not any machine instruction. It's telling the assembler, possibly the loader, where to start loading into memory, right? Right. So, and why would you want that? Because you're probably not going to have the entire image all at once. You might load in different images. So the starting address is going to be different. And so as you can guess, that's 0, and then 1, 2, and 3, and 70, 71, 72, 73, right? So that's how it does it. All right. So that's org, but this slide is really saying end. Well, end is just an assembler directive, and if you don't say end, probably nothing bad happens. Maybe a real assembler might not close a file, but some will probably do something reasonable. Anyway, it doesn't cause anything else to be generated in the assembly, and it does not mean the CPU stops running. There's no halt instruction, at least for most machines. You might have sleep instruction or sleep mode, but just because you see an end doesn't mean exit or like your main and just exit. No, it keeps running. Okay, end is directed for the assembler, not for machine code. There's no halt. There's no stop. No end program. It just keeps running. Right, and so it executes no op by default, but it doesn't have to, because if you already have memory that's used or not initialized, it could be garbage. And here we're using a simulator. Simulator tries to be nice and initializes things to 0, but a real memory might not be initialized. Okay. I'll leave that for you to find out. Try it yourself. Probably nothing bad. No, but, okay. Now, program execution. So I showed you. You can look at the PC to see where it's currently fetching instruction from and executing. Code memory allows you to switch between data memory, code memory, display. Okay? Now, you do need to know the size because in this particular architecture, data memory is 128 bytes. That's all you have. And you see the entire data memory right here. Here, data memory, right? So this is entire data memory. Say 128 bytes, that's not a lot. Well, you could actually do your whole threads package, preemptive multi-threading timer application in 128 bytes. And students last year did it. And there's room to spare. Code memory, on the other hand, is 64K bytes. So if possible, if you have constant data, put it in code memory. You can actually read from there. And you can only see 128 at a time, but that's okay. You can go and look at other parts of the memory. And you can modify code memory with a value. So give the address and then put in the byte, and then you can force some value into form the code memory. Okay, now for program execution, right? So that's where it is, and it just keeps running. And with 8051, the instructions are not fixed width. In other words, some may be single byte instruction, others might be 2, 3, how many bytes. So the PC gets incremented by the size of the instruction. So sometimes it's increments by 1 byte, sometimes by 2 bytes, sometimes by 3, depending on how many bytes that particular instruction is. unlike you may learn RISC architecture, everything is fixed, 4 bytes instruction or something, right? But even RISC have been trying to find ways to compress. Now, advantage with variable length is that the code density tends to be higher, so that your program size can be made very compact. Okay, now to understand all the details about the controller or 8051, the formal name is MCS51. I posted a data sheet, but I'll give you a quick overview. The data sheet looks like this. So if you download, that's what it is. MCS51 microcontroller family manual. And it was a scanned PDF, because back then people didn't really save PDF, and they scanned it, but they added a link so you can click. There's overview, instruction set, so you can see every single instruction, the hardware and all that, right? So you have the architecture overview. So this is a real chip, and I actually got to use this when I was an undergrad. And even nowadays, a lot of vendors, Texas Instruments, Silicon Labs, they still sell 8051 base, but they're much more enhanced. So you can read this. You might not understand everything all at once, but then use it as a reference, and we'll try to cover things. And you do want to use this as a reference to look things up. Okay, but I'll give you the quick version. So this is an 8-bit architecture. What that means is its registers are 8 bits. And it works with 8-bit units. Now, the only thing that's 16-bit would be its external memory space. So it has actually an external program memory space, external data, but then Edsim 51 does not support the external data, so you only have internal data. So it has these different address spaces. Now, internal data is something I call iData. It's only the 128 bytes that you see on the screen. And it has these separate address spaces, and it's called a Harvard architecture as opposed to a von Neumann architecture. Harvard architecture uses separate banks for data and program. Data and, so that means if I have address 20, I don't know what you're talking about. You have to tell me, is it internal data, address 20? Is it code memory, 20? Is it external data, 20? 20, what does it mean? You have to qualify your address 20 with which space you're talking about. Okay, so there could be simultaneously code memory 20, which contains totally different value from your data memory 20. And your code memory 20 probably can't be changed because it's programmed into the firmware. Okay, so these are separate code memory. So a lot of embedded processors, DSP architectures all use Harvard architecture. Now ARM is more of a von Neumann architecture. It's one space, but it's 32-bit address space. It's bigger. Anyway, so this is the block diagram. So the processor itself is only this tiny little thing here, CPU. So that's what you program. And a lot of what you program can affect the boxes outside. And then there's external control. You probably don't really need to know the details, but you do need to be aware of this. Oscillator, what does it do? Oscillator is kind of this heartbeat generator, right? So all digital systems have some crystal to generate a clock frequency. You might have like a 1.5 gigahertz Pentium thing. Well, here, no, this is a couple megahertz. So much slower, but much lower power. So it's a crystal. Crystal is this, I don't know, quartz or something, where if you run some voltage, it oscillates. It generates pulses. Very precise. Right? You have a crystal oscillator-driven watches. Very precise, like quartz ones. Some of these may be silicon ones, less precise, but still workable. Some bus controllers, like 4 I/O ports, the P0, P1, P2, P3, we would use the P1 that we talked about, right? And then serial port, which you'll be using a lot. So sometimes people call these UARTs, so universal asynchronous receiver transmitter, but you'll get to see this a lot more. So just call it a serial port for now. And there's two parts. One is TXD and RXD. What do they stand for? T for transmit, to send. R for receive. And D is data. So transmit data, receive data. Each one on its own wire. And they are independent. So that means you can turn on only the TX, or only the RX, and they just happen together independently. Okay, they do share some resources, but for the most part they are operating independent. And if you can do two-way communication, it's called duplex communication. And if you do two-way communication one direction at a time, that's simplex. No, sorry, that's a half duplex. Simplex is only one direction at a time. Only one direction at all. one direction at a time, two-way is simplex. No, sorry. One direction only is simplex. One direction at a time, but two directions both supported, that's half duplex. If you can do two-way communication at the same time, that's called full duplex. Okay, just terminology for you. This supports full duplex, so that means simultaneously two-way. Okay. Now there's also timers. There are two timers: timer 0, timer 1, and then there's on-chip RAM, on-chip ROM, or program code interrupt control. Okay, you gotta have at least this concept, and we'll be using different parts over time. So as you can see, the LCD, LED buttons, they're not part of 8051. They're outside, okay? But you connect these ports to them. Okay, data spaces. So code memory, iData, xData. So code, that's where you have the program memory. When you assemble your machine, code goes into code memory. iData, internal, that's the 128 bytes that you get to use. But you say, hey, iData, 128 is only 2 to the power of 7, right? What happened to the other part? There should be 256 to make it even, right? Everything should be 2 to the power of 8, 16, 32, things like that, right? Well, it turns out it's, yes, if in complete terms, it's 256 bytes, but then half of the 256 are reserved for special function registers. So your P0, P1, P2, they are in the upper iData space, and they are really not just for data, they're for special function. So your real data is only the lower 128 bytes, okay? And in fact, some of them overlap with CPU registers, and other things, but we'll get to see those. Now, xData theoretically is supported, but on the 8051, the original one is optional. You would have to connect an external memory unit, and in fact, wire it up with what's called these address latch. Then it can do the external data. On Edsim, this is not supported, so don't worry about using xData. In fact, if you try to use xData, it's going to say, sorry, not supported. Okay, as with any processor, 8051 has what's called general purpose registers. These are 8 bits. And conventionally, you would think in terms of R0, R1, R2, all the way to R7, right? These are CPU registers. Now, in addition, it has what's called an accumulator, and it has a name A, A for accumulator. But A is just one way of referring to the accumulator. Sometimes you also see ACC. That's also referring to the accumulator, but that's an explicit reference as opposed to an implicit reference. And I'll explain that another time. Or if you look at the instruction set documentation, you probably get this. Okay, there's A and there's B. These are also really just for your use. Although some of these are hardwired to certain instructions, so they get changed as a side effect. Each one is 8 bits. So you have A, B, and then R0 through R7. And these R0 to R7 are organized as banks. So it actually supports register banking, and we'll use register banking as a feature for your threads. But we'll talk about those later. There's one 16-bit register called DPTR. DPTR is for data pointer. And 16-bit, but then, well, how do you actually change the 16-bit? Well, you do it in two separate registers, two separate 8-bit registers. So there's one register called DPH, one for DPL, H for high, L for low. So you can read or write DPH, DPL as two separate registers, but then they are physically connected together as a 16-bit register, as a pointer register. Okay, so DPTR is 16-bit, accessible as DPH, DPL separately as 8 bits. Now, PC is program counter. You saw that in Edsim. But there's no instruction that says move PC comma something. You can't move direct. You can't access it directly like that. You can only use jump instruction call to make. So access to PC is restricted. Okay, so you can't do a move to or from PC. There's something called PSW that stands for processor or program status word, depending on the terminology. But both start with P. So these are bits that are needed by the processor to support program execution. And if you want to know detail, you can read the data sheet, but we'll talk about a few of these bits over time. For now, you just think of these as control bits used by the processor. Now, these CPU registers are banked. So you even though you can see R0 to R7, you can actually have 4 sets of these and select between them. And they map to the iData space. So you can have one set that's for map to address 0 to 7 in iData memory, another from A to F, another from 10 to 17 hex, another from 18 to 1F. So allowing you to save these registers is nice because in one case you can use one set of registers for maybe an interrupt service routine. And in our case we use one set per thread. And you'll see how this works. But the thing to do is you change these bits so that the R0 and R7 now can get mapped to a different set. A is accumulator, and it's implicit in many instructions. So add A comma pound sign 23 means A gets A plus 23. Now it's A here because it's part of the instruction. So A is not represented as any bits that you can see. It's part of the add A comma something. Okay. Now if you instead of saying A you say ACC, then that would be a different instruction. Your reason for using A is it enables very tight encoding. There's only one. You don't need to encode it. It's part of the instruction. Anything else that explicitly references register would have to be encoded separately. So machine instruction, think of it as tiny function calls, except you have opcodes instead of functions, operands instead of arguments. Okay, and these arguments can be accumulator, register, constant value. If it's constant value, put the pound sign in front, right? Value memory. Okay, these are the opcodes in 8051. If you're interested, you can read that data sheet. So there is instruction documentation. So the program memory, right? So this tells you all the detailed interrupts, how things work. So we'll go over some, but then we expect you to also be looking things up. Yeah, here it will be an example of documentation. So yeah, it tells you the formats, register, the notation, like add here. So you have one instruction that's add A comma and then the register. It's only single byte, takes 12 oscillator periods. There's another form of add, takes a direct address. One takes a at R, so that means dereference the address in register RI, or you can add with the constant data, or that's called immediate. Right? So you can add with the carries. So these are where you can find the explanation for the opcodes in 8051. And sometimes they show up in different versions. You have move, add, and then rotate, increment, no op, jump, call, and then jump conditional, and so forth. Some with side effect. Okay, so real quick, this is Intel notation I already talked about. Pound sign indicates constant. H is the hex base. Without H, that's assumed to be decimal. But because of the limitation at the time, pound sign followed by something has to be either numeric or symbolic. If you do pound sign FF, you say, hey, FFH, that's hex FF, right? No, it doesn't interpret that way. Because it sees it's a alpha, right? So that means a letter. It thinks it's a label. In assembly, you can have labels. So it thinks FFH is the label, and then it tries to look up what FFH, that label, is. Well, that's not what you want. So if you want to be constant FF, then you have to put another 0, kind of a useless 0, but just so that it knows to interpret it properly. But you can also do pound sign -1. That's the same thing. That's what I do. Anyway, that's a little thing you should remember. And immediate versus indirect, right? Pound sign versus no pound sign. This came up a couple times already. Pound sign means it's a literal value, so the value is 17. Without pound sign, that's the address 17 hex. Okay, big difference. Move instruction, source, destination. Okay, and so think of it kind of like an assignment statement. Destination gets source. Move, destination, comma, source. Right. All right, and then move has these variants I showed. You can look at the data sheet just to see explanation. And then there are combinations allowed. Some combinations are not allowed. So you can do register to register move. Move R1, comma R2, not allowed. You have to go through A. So move A, comma, register, and then from the register A to that, to register the target register. And you can't do move A to A, that's useless. Or move immediate, comma, register. You can't override a constant, right? So some combinations are not allowed. Okay, so yeah, due to time limitation, I'll continue with this, but you can look through the slides yourself, download, try playing with this, make sure you understand things so far before you go on to the next steps.